Hey, we're checking out the fundamental theorem of algebra today. So, the fundamental theorem of algebra says any polynomial of degree n has n real roots. And those consist of real or complex roots. So here's an example. If I have g of x is equal to 4x cubed plus 2x squared minus 7, I'd have a function that looks something like this. This is a rough sketch. Notice that the graph is touching the x-axis 1, 2, 3 times. You can, but it can't touch it more than that. This function has 3 real roots. So a degree equals 3 can have 3 real roots, 1 real, and 2 1 real and 2 complex. Okay. Something to note is that if you have complex roots, you always have 2. They always come in pairs. So for example, if we have x equals 7 minus 2i as a complex root, then we automatically have another one of x equals 7 plus 2i. It's a complex conjugate. Okay, let's do some examples. Find them. All right, so we're gonna write the equation of a polynomial with roots of 4 and negative 2 plus 3i. We're going to write them in factored form and then in standard form. So I know that I have roots at x equals 4 and x equals negative 2 plus 3i. Remember, we're a third degree polynomial, so how many roots should we have? We should have 3 roots. I have one that's complex, so I'm going to have a second that's complex, negative 2 minus 3i, my complex conjugate. We're going to set this up as in factored form. And since our book uses some language like as a product of linear pairs, so no quadratics, it means that they want you to factor this equation out all the way into complex roots if we can. Okay, so we're going to write, let's call this m of x is equal to, start with my real root, x minus 4 times x minus my next root, negative 2 plus 3i, times my last root, x minus the root. Okay, we shall distribute. I'm going to distribute the negative sign into both of these, so I get x plus 2 minus 3i times x plus 2 plus 3i. And that's a little cleaner. All right, whenever I multiply out, so this equation right here is in factored form or a product of linear pairs. Each one of the x values has a degree 1. So each one of the factors looks like the equation of a line by itself. Okay. All right, we're going to multiply these out. I always go for the complex roots first. I'm going to multiply out these two. So I'm going to use area model because I think it organizes myself a little better. So I'm going to do x plus 2 minus 3i. I have 3 terms, so I'm going to use 3 rows and 3 columns. Okay, x times x squared, 2x minus 3xi, 2x, 4, yep, negative 6i, positive 6i, ix, excuse me, Nope. X times 3i is 3ix. And then 2 times 3i is 6i. And then I get negative 9i squared. You should have a bunch of stuff that cancels. So the xi's will cancel. And the plain i's should cancel. And then I'm going to go ahead and change this, since negative 9 times I squared is basically negative 9 times negative 1. I'm going to change this to a positive 9. So I get x squared plus 4x plus 4 plus 9. So x squared plus 4x plus 4 plus 9. All right, let's go ahead and write this in our, just so we can see what's going on. I still have x minus 4 as a factor, and now I've combined the imaginary factors to give me x squared plus 4x plus 13. I'm again going to go ahead and multiply. So I'm going to use area model again. I'm going to do x minus 4 on the side, and on the top I get x squared plus 4x plus 13. Each term gives me a different column. So I get x cubed plus 4x squared plus 13x minus 4x squared minus 16x minus 52. So m of x is equal to x cubed, combine these, plus 0x squared minus 3x minus 52. And this equation is in standard form. All right, next one and last one for today. Here we go. So for the function, now we're going to deconstruct our standard form equation. So this is standard form. And we're going to write it ultimately as a product of linear factors. So remember, we're factoring. So here's what I do. I first sketch the graph as A. We're going to sketch the graph. I really had to adjust my window. So it looks like a straight line when you graph it, but it does have a very fast increase here. So I noticed that I have a root at x equals 0, or an x-intercept. Okay, a rational root. So I can, since this is a third degree polynomial, I can divide out this root and I'll end up with a quadratic. And we're super good at dealing with quadratics. So that's to our advantage. So let's go ahead and do that. I'm going to divide out for b. I'm going to use synthetic division. My root is 0. And my coefficients are 1, 10, 169, and 0. Remember, the last box is your remainder. I'm bringing down my 0, 1. Bring down my 1 times 0 is 0. Add 10 times 0, 0. 169 times 0 is 0. I get a remainder of 0. So that's good. We know that x equals 0 is a factor. So g of x can be written as x times x squared plus 10x plus 169. I am now to the part where I am going to factor this quadratic. How do you factor quadratics? Big X, quadratic formula, or any other method that you can think of. Changing to vertex form and solving for x. Okay. I can see right away that I can't use the big X, so I'm going to use quadratic formula to factor this. So we're going to do the quadratic formula. Okay. So I get x is equal to negative 10 plus or minus the square root of 10 squared minus 4 times 1 times 169 all over 2 times 1. I get x is equal to negative 10 plus or minus the square root of negative 576 over 2. So 576 is a perfect square. It is 24 times 24. And then since it's a negative, we're multiplying by negative 1. Square root of negative 1 is I. So I get I 24I over 2. Then we're going to divide to simplify. Make sure you divide into both terms. So x is equal to negative 5 plus or minus 12I. That means that my roots are x is equal to negative 5 plus 12I, negative 5 minus 12I, and 0. I can write my equation as a product of linear factors, like so. I think this is g of x. So g of x is equal to x minus 0 if you want, times x minus negative 5 plus 12I times x minus negative 5 minus 12I. And then let's clean that up a little bit by distributing in the negative sign into both imaginary roots. So we get x times x plus 5 minus 12I times x plus 5 plus 12I. And that is as a product of linear factors. So I got roots and a product of linear factors. That's what we do.